It is my pleasure to give a talk here, and I would like to thank the organizer for invitation. The title of my talk is Garography, the global garography. So let me first say a few words about applications. There are two main applications. One applications deal with description of quark-gluon plasma, and the second one concern condensed matter. So the outlook of my talk will be the following. I will start from telling you about garography and so-called ADS-CFT correspondence, and this will be described in the so-called Poincare coordinates. Then I will explain what means global garography. Roughly speaking, it's just a garography on the group manifold. And then I will give the simplest example. First of all, I will speak the simplest, what means garography? It means that we can calculate something in, for example, in 4-dimensional space-time using something in 5-dimensional space-time. So I will describe you several examples. One example concerns empty ADS space. Then I will speak about ADS with black hole, and then in ADS with particle and with moving particle. And the last two examples deal with 3-dimensional case. 3-dimensional case is in some sense exact integrable case, because in this case gravity is a topological model, and so we can do many calculations rather explicitly. And as an example of application of global garography, I would describe your applications in some very exotic example, so-called God time machine. As well, I will speak about collision of ultra-relativistic particle. Okay. So let me start from remind the definition of anti-de Sitter space-time. The n+1 dimensional anti-de Sitter space-time is just a hypersurface embedded in Minkowski space. So in Minkowski space we have this metric. We deal with signature 2 n in n+2 dimensional case, and our hypersurface is described by this equation. We can introduce the coordinate. An explicit formula is written here. So the induced metric on anti-de Sitter space-time is written here. Let me tell you two very peculiar things. First of all, you see in this reduced metric, in this induced metric, there is one time coordinate. This coordinate called tau. But if you look on this explicit formula, you will see that tau is a periodic coordinate. Of course, we can deal with covering space-time, and we will do in what I'm going to tell you just in the half of my talk. Okay, what we can see immediately from this explicit formula, we can say immediately that there is a boundary. In these notations, the boundary corresponds just to the case when this cos equal to 0, so this is a special value of rho. And this means that the boundary of anti-de Sitter space-time is exactly the circle cross a sphere. But if we deal with covering space-time, covering is written here, so we just remove this periodicity condition and consider the line for tau, then our boundary look like this. And if we deal with Poincaré patch, so if we take just 1/2 of anti-de Sitter space-time, we can think that we take just 1/2 of a covering, then in this case the boundary is nothing but as n-dimensional Minkowski space-time plus some other special region. And from physical applications, the more interesting for us is this case, because the boundary is just our Minkowski space-time. And according to holography, we're supposed to describe the theory on the boundary using some information inside the manifold. Let me remind the main formula for RDS-CFT correspondence, which is a formula was realized by a very famous paper by Gapser, Klebanov, Polyakov, and another paper which came almost simultaneously by Witten. And according to this formula, to calculate the correlator, this is generating function for correlator. What is written here? Suppose that O is some operator with 5, 0 is a classical function and like some current, and we integrate on the boundary. And according graphical prescription, to get this answer, it is enough to calculate some classical action which depends on the metric. The metric should be a metric on some manifold. As a manifold, we can take anti-de Sitter or Poincaré anti-de Sitter or black hole in anti-de Sitter. And the boundary of this M, this is our space-time. So if we're supposed to consider some lattice field theory on the sphere, we for sure have to take anti-de Sitter case. If you want to deal with Minkowski space-time, correlating Minkowski space-time, then it's reasonable to take Poincaré anti-de Sitter space-time. Okay, what is written here? Here is written some classical action. This action depends on some scalar field, for example, and J is a metric in this manifold. We're supposed to solve the classical equation of motion. So this is a non-linear, in general case, some non-linear differential equation written in the given matrix. And for this differential equation, we're supposed to solve the Dirichlet problem. So we have to specify this FC, C means classical, this classical field on the boundary, exactly this boundary, and it's given by this current. This current, I use 5, 0 to denote this current. And in another more special case, when we deal with black hole, this boundary condition is not enough. We have to specify some behavior of our classical solution near the horizon. But roughly speaking, the prescription is the following. I think it's clear. If we want to calculate some correlator, we have to calculate, we have to solve the classical equation, and we have to solve a Dirichlet problem for this classical equation. Okay, you can ask me why it's work. Instead to answer to this general question, it's difficult to tell you a general arguments why it's work, and of course it's supposed to be work in conformal case. So this means conformal. So this theory we describe as correlator should be a conformal invariant or very close to be conformal, or some small deformed conformal field theory. Okay, instead to give you general arguments, let me consider a few examples. And to give you with few examples, let me also do some simplification. So instead to solve a Dirichlet problem, so this concerns just a solution of some classical equation, we can use geodesics approximation. This is a very useful tool. What means this geodesics approximation? According to this version of holography, with IDS-CFT correspondence via geodesics, means to calculate some correlator, for example, two-point correlator of some conformal field with conformal weight delta. We have to do the following. We have to take our d plus one dimension model for gravity. For example, and for this particular case, we have to take a Poincare manifold with Poincare boundary. And we have to take 2 points on the boundary. Here I wrote especially some special case when we consider equal time correlator. So this is just a space point x and x dot. And I have to fix these 2 points on the boundary. The picture is just for three-dimensional case, but we can imagine any dimensional case. And we have to calculate, and we have to draw the geodesics which connect these 2 points. And we have to calculate the length of geodesics. And the answer for correlator should be look like is written here. With L is a geodesic length. But there is some non-trivial point here. Instead to take just a geodesic length, we have to take renormalized geodesic length because there are some divergences, and the prescription is very simple. We just move our point from the boundary on some direction, for example, to the point is here, the boundary is zeta, z equal to 0. We have to go to some point zeta 0 and calculate with geodesics and then perform some renormalization. This prescription was proposed already many years ago, and in the next slide I would like to show you how it's worked in four-dimensional case. The answer for conformal correlator in two-dimensional case is written here. Once again, this is the answer for equal time correlator. This is a conformal weight. And we can calculate this, in this case, the geodesic length. Here is written explicit answer for renormalized length of geodesics. Here it should be written also vacuum. The answer is look like this. So if L is small, then we get some logarithmical divergences. But if you remove divergences, we end up exactly with this answer. Let me show. Okay. The next example deal with black hole. We can consider more complicated manifold. We can consider so-called black brain in the Poincare coordinate. So how it looks like? If you take f equal to 1, we just reproduce the usual Poincare metric. But if you write some function which is written here, this is the answer for three-dimensional case, for the case when dimensional spacetime is moving, it would be, we have to change the power here. But in three-dimensional case, the answer is here. And RH, this is the position of horizon, which is related with Hawking temperature. And if we calculate the length of geodesics, also perform some renormalization, we will get this very well known answer. This is the answer for correlator in the presence of temperature. To get temperature equal to 0, we have to perform expansion here and also use some normalization coefficient which depends on t. So I think it's absolutely clear. So what gives us a holography? Holography in this geodesics approximation tell us that study a simplest from a mathematical point of view problem, study of geodesics, can help us to understand what is going with strongly coupling system. Of course, holography first of all was formulated for n equal 4 theory, this is a very special theory, which is in quantum conformal invariant theory, but now is widely applied in more complicated system. What is the reason? What I'm going to say, say a few words about quark-gluon plasma, and just remind you that quark-gluon plasma is a matter formed from the confinement quark and antiquark and gluon at high temperature. Of course, this theory is supposed to be described by quantum chromodynamics.
Value of temperature for the confinement.
This is experimental quantity, and we can what people are doing. They can in chromodynamics, for example, we can doing some lattice calculations. We can calculate the temperature, with the confinement temperature for QCD. It's a very well-known answer, about several hundred MeV in energy. In energy scale. Okay, of course, unfortunately, the dual description of quantum chromodynamics does not known, and N equal 4 theory is not the same as quantum chromodynamics, but there are some similarity between quantum chromodynamics and N equal 4 at high temperature. It's also the results coming from lattice calculations, result mentioned here. These calculations tell us, then this is exactly the answer to your questions, then temperature is more than 300 MeV, then lattice calculations show that quantum chromodynamics has equation of state, which is written here. E is energy, and P is pressure. So this is a typical equation of state for conformal matter. And so we can try to use. This is a give a reason exactly. This lattice calculations give a reason for people to use a graphic description for quark-gluon plasma. This is a very big activity in this region of more than 1,000 papers were written. And why it's so interesting? First of all, due to experiments on the RIC and LHC experiment, people found that quark-gluon plasma is strong coupling fluid. So in principle, perturbative method cannot be applied to describe this new state of matter. Second, because we want to describe a thermalization. You know, it's very difficult in general system to describe thermalization, especially in the case we deal with strong interacting system. And also, if you want to describe thermalization, you cannot use a lattice formulation, because this is a real-time problem. And the lattice formulation of QCD deal usually with Euclidean version of theory, with Euclidean version. So this is just a good problem to use gauge string duality or ADS-CFT duality to describe quark-gluon plasma. So, and there are two main regions for this applications, to application of ADS-CFT to plasma. The first is concern graphic description of quark-gluon plasma in equilibrium, and the second branch concerns this graphic description of formation of quark-gluon plasma in heavy ions collision. Of course, this problem is essentially more complicated. But how we can try to solve this problem? I have shown you an example of two-dimensional example with thermalization, or in other words, the correlate at high temperature can be obtained due to calculation in some anti-de Sitter space-time with black hole. So, if I want, I can believe that if I can describe black hole formation in anti-de Sitter space-time in d+1 dimension, then due to holography, maybe, I would say, I can describe thermalizations in Minkowski d-dimensional space-time. What can be the profit from this approach? First of all, from the study of black hole formation in d+1 dimensional case, we can expect to find a time of thermalizations in heavy ions collision, and also we can try to calculate the multiplicity, which is just a number of particles produced in heavy ions collision. All numbers, this is just experimental data. So,
Minkowski d-dimension, it's a boundary.
With Minkowski is a boundary. Yes, after this. Today I will speak not on the Minkowski, today I will speak mainly about the circle, but like some kind of toy example. But the main problems are related with Minkowski space-time. And to be honest, I have to mention that the problem of black hole formation in Minkowski space as well in anti-de Sitter space. This is a very difficult problem. This is a classical problem in general relativity, but it's a very difficult one. And now, today we know just some numerical evidence of appearing of black hole, for example, in 5-dimensional case. Because if you want to deal with 4-dimensional case here we're supposed to deal with 5-dimensional case. So this is a very complicated question, but people are studying this numerically, and what people do with numerical calculations, they use a global coordinate. So this gives me a reason to study in some the same problem in 3-dimensional case, also in the global coordinate. And what is how we can expect to get black hole formation, and who will control the black hole formation, or better to say, who can initiate these black hole formations. Let's take some 5-dimensional metric. This is, for example, what you called background metric. So it could be, for example, anti-de Sitter metric in 5-dimensional case. And suppose that we make some perturbation in 5-dimensional case, and this is in the beginning of time, and then we're supposed to get some, maybe to get some black hole. We can study this problem in general setting, but this is not exactly what is interesting for us, because according to the CFT correspondence, we have to look for some special perturbation. And the requirement of this perturbation is the following. Our requirement is the following. We take this perturbation, put it on the boundary, and take only 4 coordinates. So m and n go from 0 to 4, and mu go from 0 to 3. And we make some renormalizations, we know what we have to do, and we get some energy tensor. So with our requirement that this energy momentum tensor in 4-dimensional case should be in some sense remind the physical situation which we would like to study in 4-dimensional case. This is general setting. To be more precise, I will show you what does it means in some particular example. As some kind of perturbation metric that there are several proposals to deal with in the literature. The simplest one with the consideration of so-called infalling shell. This is an interesting proposal. We can do some explicit calculations in this approach. A more realistic case is a consideration of shock wave, but technically is not so simple, but several works was done. Our group is also participate in this activity. And the simplest example, which I supposed to describe you today, I will consider the collision of particle in 3-dimensional anti-de Sitter space-time. So, What is a model for us? From this general setting, it means that I supposed to describe thermalization procedure in two-dimensional conformal theory. So this would be our goal. Example. So we will consider collision of particle in three-dimensional case. This problem of describing of particle in three-dimensional Minkowski space was studied many years ago by Hoft, Deser, and Jacquev. So if you supposed to solve Einstein equation of motion, which have some energy momentum tensor corresponding to particle, point particle, which is stationary particle, then the solution is written here. This is a mass of the particle with a gravitational coupling constant, which you can read from this formula. What is interesting? We can perform the transformation, and we can find that this metric, which people found, with nothing but as a consingularity. So we can rewrite this metric as a flat matrix, but in polar coordinate, but your angle will be not from 0 to 2 pi, but there is some deficit angle. So this is a general property of point particle. This is just a main feature, we can say. This is due to the fact that gravity in three-dimensional space is essentially more simple. This is a topological model. So in some sense, we can say this is just a topological effect. And the same is true for de Sitter and anti-de Sitter case. And we can say that particles are described by the angle deficit. So what I am going to do, I will consider anti-de Sitter space with some conical singularity. I will, to describe collision of two particles, I will consider two conical singularity and look what I get on the boundary. And we'll calculate the correlator which corresponds with procedure. This is, all calculations can be done explicitly. And this is due to the fact that anti-de Sitter very convenient here to use description in group manifold. You know that these three can be considered as SL2R, and the point of our space-time now is this metric. It's written in coordinate, free coordinate. This is a time. This is, you see, this is periodic time, but we can ignore this periodicity. This is the angle variable, and also the radius. As immediately you can see immediately that there is the boundary is at point r equal to 1. The matrix in anti-de Sitter space-time is a Killing-Corton metric, and it can be written in this form. Who knows, the Schwarzschild solutions can be. It's not exactly the same, but maybe get some idea about it. So, how it looks like? We can imagine our anti-de Sitter, three-dimensional anti-de Sitter space-time and global coordinate as a cylinder. So R goes from 0 to 1. Here is a boundary. 5s go from 1 to 2 pi, and T goes from, I will consider from minus pi to pi, and I will not assume that this circle this disk is identified with that one. Okay, what we get for particle? If we consider I forgot the existence of the doesn't matter. If we consider the stationary particle at the center of cylinder, what means this picture from previous point of view? It means the following: if I take a fixed time, so I take a session. I take a section here. This is a picture for this section, and I put a particle here. So suppose that I have this deficit angle, and I would like to calculate the correlator. If on the boundary I take the point A and point B. If A and B are very close to each other, then of course I can geodesics with minimal length is nothing but this red curve. But if the point B is far away from A, maybe I have to calculate the geodesics between image of this point A. So let me consider this picture. So I take first point B here, then here. So obvious the length is here, and this is a red line. This is the length between A and B. Because I identify A with A star, then I can also calculate with blue geodesics and its length. This length is written here. It's absolutely obvious that at some position these two geodesics have the same length. And if I make some competition between these geodesics, then the answer will look like this. Of course, you can tell me, oh, why you take one geodesics approximation? Maybe you have to take two geodesics approximations. In this case, I can tell you then if I take with conformal weight big enough, then the geodesics approximations is very good approximation. Then delta equal 1 or other small number, then it is more reasonable to deal maybe with two geodesics approximations. So here is written the answer. For correlator, for in the space-time, in the present of stationary point at the center. This is the explicit answer. It's not a big deal to write down. This is just a sin square of this angle, but the picture is presented here. Okay, now. Because we are going to discuss in somehow in four-dimensional case some moving objects, for example, some ions. So we have to be able to just calculate the correlator for moving particle. And I will show you the formula which describes the moving of particle along some special curve here. And why it's so special? Of course, this conical singularity should be isometry of conformal group, and as the result of such identification, so this is a particle move here, and instead to remove simplest wedge as was shown in the previous slides, here I have to remove the wedge between this phase and that phase. I will show more explicitly in the next transparencies. So what means this picture from the boundary? This means that I have to remove some black part here, and this black part move during the time. So this is so-called dead area. And I will be able to calculate, I'm able to calculate the correlator on the boundary and to analyze this problem. To describe the geometry behind this simple picture, we consider the moving of a particle along the spiral, and we get this spiral, we start what I said, from stationary point, with position in space-time for this stationary point is described by this metric. If you want to deal with moving particle, we perform the Lorentz boost, and so I have to consider the identification of these two wedge. This is wedge number 1, which is written here, and the second phase will be similar, but I will take plus here. So the picture looks like this. This is our cylinder. This is the first wedge. This is the second wedge, and here is a picture for the session. And as was recognized by Gott many years ago, that if with deficit angle, the sum of two deficit angles, if you consider not identical particle, is this deficit angle is more than 2 pi, then you will get a time machine. And we can look the correlative function.
Where are you going? Back or forward or back?
It depends of your deficit angle in the future. Here will be here will be a time machine in the future. So this is a very simple thing. This is just some kind of lensing effect. This is just an effect of a removing of some space-time. So here is a cylinder. You identify with phi equals 0 and phi. Oh yes, here is phi equal minus pi. Here phi equal to pi, and you identify these two lines. And you don't identify here the top and the bottom, and because you have to remove this area. The identification vector is shown by this dash line with vector, the dash vector. And for example, if you alight, you go like this with light velocity, then you can jump back in time. Then you continue in the future, then you go back. And if this deficit is big enough, so if this area is big, then you can get at the same time that you started from. Okay, thank you. I will. So, how it look? Why you cannot take just one point? Because there is, for one point, if you take for another point 0, and the first one, I tell you, its deficit angle should be more than 2 pi. You cannot imagine some type of situation. So it's the reason why you have to take two particles. And if you, for example, increase the deficit angle, then in some time you can realize that you do not have a space-time for living at all. You have no boundary. And in some sense you can say, okay, there is some kind of singularity. And to increase the living space, you can just push this point close to the boundary, which means you increase the Lorentz parameter. And the whole picture looks like this. So this is a typical picture for space-time, for good time machine. And what is the answer? The answer is very simple. This is the answer for inverse correlator in one geodesics approximation. This is the answer for correlator on the cylinder. This is we use the image method. This is a contribution for image point, and you have to take the minimal length. This is presented by this tau Heaviside function. And this is the identification vector, tau 0, which you can write explicitly. And we did these calculations and found that inverse correlator look like this. And correlator themselves, they look like this. And you have the picture for what is the meaning of this? What is the meaning? What we get? Of course, it is almost obvious from the problem itself that if the deficit angle is big enough, then we get some situation on the boundary, then there is no causality at all. It means that if you draw the light cone in some area, the living area is just the area for this green parallelogram. And for example, in this, you don't see any light cone except the boundary. But here, in any case, you have a light cone. A light cone goes from on the left. This is there are everywhere this blue point. At some region there are two blue points, but here there are some regions where there is no blue point at all. Okay, now we can do the same for maybe more realistic case, which deal with collision for ultra-relativistic particle. In some sense, the problem is more complicated here, but the isometry also is described by very simple matrices, and on the boundary there is the identifications between this the point T map. I will draw you. Maybe I will skip. And I will show you the picture of collision of two particles. So here we can live only on this green part, but still we can live. And so our space-time look like a cylinder with a waist, or if you want to say somehow hourglasses. I will finish maybe in 2 minutes. And we can try to calculate the correlator. Of course, we can use the image method here, and we can search for the difference in this picture when there is no black hole, with a picture when there is a black hole, and maybe this is I will skip, and you will see if I take this angle big enough, then at some moment there is no space to live. So we can say that there is some singularity which can be interpreted like a black hole formation in this particular case. So what we're supposed to do in high-dimensional case? Because in our case, our living space is flexible. We can suppose that in high-dimensional case also we can deal with some kind of container with flexible wall, and its picture roughly remind what is going with heavy ions collision, because heavy ions collision we have two Lorentz contracted disks, and we have these two disks are at the beginning at some distance, then they collide. So we can think on this area like some area inside some container with flexible wall. So I can. But what is the difference in the picture? In two cases, when there is a living space on the boundary or there is no living space, I can, in the case that there is some we call this thermalization time, the time at which there is no boundary at all. If I send the light from this point, for example, I reach the boundary. If I send the light from the point more close to the center, then I will never reach the boundary. I can say that there is appearance of a trapeze surface, or roughly speaking, a black hole. In this case, I can also calculate the correlator. So what I have to do if I want to calculate correlator between these 2 points, I calculate the length, renormalized length of geodesics. I also consider the image point and calculate the correlator. And this is written the answer. And of course, I have to know this map. And the vector field which describes this map is presented here. This is for the case when we do not expect a black hole. This is for the case when we expect a black hole. I cannot say that this picture is more smooth, generally speaking. But it happens. I will show you a picture, and this is a picture. This is just explicit. Everything is explicit. This is some complicated formula. And I can we calculate the correlator, not we, but this is mathematics. What is here? Red is a correlator function for 2 points. Blue for 1 point. So we don't see any regularity here. Here the case when we expected to see a black hole. Nothing look special, but this is yellow. This is exactly the thermalization picture. So this work is not finished yet because we have everything explicitly. So we expect to get everything is explicit, but we cannot explicitly write that in this region we get this asymptotic so on. So we are going to do this. So as a conclusion, for what we really can calculate, we can, in this particular example, we calculated the thermalization time, and what we supposed to do, we're supposed to compare our correlative function with correlative function which was obtained in more simple and less realistic model. For example, the model which use ADS metric, VADI-ADS metric as well. We suppose also to make calculations for non-central collision, because in this case I describe a collision of two particles with zero impact parameter. Okay, so I will stop here. Thank you very much.